Thank you. Thank you, Dr. Chitra, ma'am. I'm audible, Chitra, ma'am?
Yes, ma'am. Yes, ma'am. You can proceed.
Okay. So, dear participants, good evening to everyone. We will move on to the next session. The next session is going to be handled by Dr. Jayalakshmi from Vidya Peetham, Chennai. So here we are having the small introduction about her. So it is my pleasure to introduce Dr. J. Jayalakshmi, a senior assistant professor at Vishwa Vidyapeetham in Chennai, India, with a PhD in information communication engineering from Anna University. She is an accomplished researcher and educator. Dr. Jayalakshmi has a strong research portfolio with several publications in reputed SEI journal, Scopus and Web of Science indexed journals, along with multiple book chapters published by John Wiley, IGI Global, and Taylor and Francis, and also the CRC Press. She is also an active reviewer for esteemed journals and conferences, including EAI Transactions on Scalable Information Systems and South Asian Journal of Social Studies and Economics. Beyond research, she is a sought-after speaker, having delivered invited talks on machine learning across various technical institutions. She has also played a key role in faculty upskilling programs and student training workshops in big data, machine learning, and deep learning. A lifetime member of the Computer Society of India, Dr. Jayalakshmi has been recognized with the Active Woman Participant Award for her contributions. Her area of expertise span artificial intelligence, data analysis, social media analysis, healthcare analytics, and more, making her an invaluable resource in the field of AI and data science. Now, we together welcome Dr. J. Lakshmi ma'am for her session. Ma'am, welcome you, ma'am. Kindly
Thank you, ma'am.
take over the session.
And very good evening, one and all. We share my slide.
Ma'am, your screen is visible, ma'am.
Okay.
Just you check to move whether the screen is sliding or not. Just we will move on to the next slide. Just for a check. Yes, ma'am, it's moving. It's moving.
It's working.
Yes,
Okay.
thank you.
So today's session, I welcome you all to this evening session, and we are going to discuss very little about AI in drug discovery, accelerating the development of new medications. So I have segregated my presentation to three sections: generative AI as such, use of generative AI in drug discovery, and then a little demonstration of how we are going to use it. So let's start out with generative AI. Generative AI has become pervasive these days. It is in every part and parcel of our life. It is artificial intelligence generating data in literally any form: text, image, sound, video, anything. And this is revolutionizing the era of technology these days. So, where does generative AI fall? AI is not a new field. It has prevailed right from 1956 for decades. It did have a winter in between. When neural network evolved, it came back to light and started back its evolution. And we can see a timeline over here: artificial intelligence. It is the broad area in which we have machine learning and deep learning and generative AI within. So these are very prominent tools we have already come across in our lives: Copilot, Bard, R, Gemini, DAL-E, ChatGPT, Llama. All these are literally known to any person these days. And so is generative AI. penetrating every part and parcel of our day-to-day life, and is a brief history of artificial intelligence, right from the Turing test, and it goes on with the development of Eliza, the chatbots, which were literally not actual chatbots in 1960s. They were conversational engines, part of expert systems for diagnosis. Uh, they then came the concepts of deep blue chess engines. Even now, chess engines are very prominently used. And right from 1990s, the evolution of AI and generative AI, it took a very uh, huge pace. And today we are seeing very many applications these days with OpenAI. Uh, there was a buzz about DeepSeek, and a lot of applications are coming into existence. These are the general use cases of generative AI. uh, Generative AI can be used literally, you can see what not, literally everything: art, content generation, NLP, finance, healthcare, medical image synthesis, and literally any part of life. So there are types of generative AI models. So what creates the generative AI models? We will see a little intro, and then we will pass on to how we use them in drug discovery. So types of generative AI models, there these are inherited from deep learning models. These are transformers which are using the attention mechanism, which focuses on certain sections of data and extracts features, and it's able to manipulate them. So this goes ahead and manipulates. It is very powerful with the sequence of sentences, and it is having an LPS the base. This is a little architecture showing how transformers work. And coming to the advantages, the efficiency of transformers, the contextual understanding, the versatility of handling any type of data, all this is the advantage of transformers. And the disadvantage being lack of interpretability, high computational and memory demands. And then comes GAN. This is generative adversarial networks with two parts: generator and discriminator. The generator creates realistic data. For example, it is very much prominent in images, and even in deepfakes generation. So it creates as many images close to the input, and the discriminator tries to find which is real and not. So these two act hand in hand in adversarial manner, and they are going to be used for classification of data. So this is a small architecture of GAN showing the generator and the discriminator along with the training data. The discriminator using the backpropagation model to adjust the learning and find the actual match, actual true data. And generative AI has very high quality data generation, and it is also versatile in nature. And disadvantage of GAN being computational cost and training instability. And then comes the variational autoencoders. Variational autoencoders also have two units, encoder and decoder. They are able to convert data to compressed formats, and they are able to reconstruct them as well. And they are very widely used in manipulating text. And they can also be used for multimodal models. Multimodal data analysis involves analyzing data in different formats with text, video, audio, pictures, structured tables, literally anything. And we can consider GPT for an example. It is able to take we can load data, and Gemini is able to load YouTube videos and give transcripts of it. So this being multimodal models, and attention-based models are very special. They have revolutionized the concept of transformers and transfer learning concepts. Along with LLMs, they play a very important role in NLP and text analysis, uh, also data in any other format. The attention mechanism is able to help us concentrate in certain segments of input that we are processing. And in a fine-grained way, we can analyze the features from complex data. So this is the power of attention models. And we are able to see a text being focused, split, and processed with the help of the model. The advantage of attention model is increased information manipulation and comprehension, and we can have larger range of dependency. Like if it is a longer sentence, still we are able to analyze it, and the flexibility of the model, and the computational overhead and the sensitivity to quality of data that we feed in as input, that is being the disadvantage. The RNN, LSTM, GRU, these models, they are very helpful in NLP because they are very strong in handling text data, text sequences, processing sequences, sequential data. They are able to uh, RNN, just being the pioneer of LSTM and GRU, this uses the hidden state that takes the prior information and, like back propagation, it's able to analyze the present sequence along with the past sequence and interpret the data. This is a very small architecture which shows the RNN along with the gates and the memory functions, the sigmoid functions, all these things. And this is the architecture with also showing the correlation of LSTM and GRU as compared to RNN. The RNN therefrom evolved LSTM and GRU with the modifications in architecture. So this is a small architecture. And coming to the advantages of RNN, it is very much useful in sequential tasks or text. And LSTM, it is having long-term dependencies and can go ahead and analyze longer sentences or complex sequences. GRU is very fast, and that is giving the edge over LSTM. And the challenges that we have with RNN, LSTM, and GRU are listed here. RNN has the vanishing gradient problem, which limits its dependencies. Like it can not manipulate very complex sequences as compared to GRU and LSTM. And LSTM has the high computational cost, and GRU has the performance overhead. And auto-regressive models, these are also very much helpful in analyzing the sequential outputs from several phases of the data processing. They are very much flexible and dynamic, and they are literally modifications of RNN and CNN. And these are models that are given autoregressive and non-autoregressive models. The feedback that differentiates both is shown here. And the advantage of autoregressive models in generative AI gives the high quality output. The simplicity of the architecture also powers the performance, that being the edge, giving the edge of advantage. And the disadvantage of autoregressive model is the slow inference and the limited contextual understanding as compared to transformer and tension-based models. And this is a diffusion model. when it comes to diffusion models, they are making a model resilient to noise. They are based on attention models, but the general principle is adding noise to the input image and making them resilient to work even in the presence of noise, like retrieving good results. So diffusion models have two processes, forward diffusion process and reverse diffusion process, gradually adding noise, Gaussian noise to the input, and then going ahead and distinguishing the data as forward diffusion. And the reverse diffusion is denoising the entire noisy image. And how it works, this is going to this is generic, which is applying to both the models of diffusion framework. So we are going ahead and training the model with the input. It can be considered an image over here. And during training, we are going to predict the noisy section and contain the interruption in the classification, for example. And when it comes to generation, we are iteratively denoising the image and we are trying to predict the noise section and remove it. So these are summaries of all the models that we discussed, and the advantages and disadvantages of diffusion models are given here. Diffusion models are very high quality and they are very stable in training, and they are also versatile with the type of data. And coming to the disadvantages, they have high computational cost, but that is being overcome. The issue with LLMs and the generative AI components has been the computational overhead that is being overcome recently with the usage of just not even NVIDIA, just the existing architecture hardware requirement that is available in a normal laptop or desktop computer. That is being the talk recent buzz with DeepSeeks. So such models are evolving, which are still to boost the usage of AI in literally any field. And then comes the LLM, large learning models. So these are powered by transformer architectures, and they are fine-tuned to work with any language-oriented issue like summarization, translation, question answering, just about anything. They are going to deal with language chains, and they are being processed using the prompts being the questions that are put up to the language chains, the LLMs. And large language models have very good understanding and comprehension. They're versatile with the type of data and also scalable. And the disadvantage of LLMs is the computational issue, the bias, hallucination, the penetrations, the security issues, and difficulty of fine tuning. All these are the issues. And sparse attention models, they are reducing the overhead that are involved in attention models and making them much cheaper. And revolutionizing over LLMs, SLLMs, and RAG models are very recent ones. Retrieval augmented generation allows the usage of data base, knowledge base, or database to be linked with the inference to make real-time analysis, because LLMs have to be pre-trained with just the tasks that they are programmed for, that limits their usage. And RAG models have an advantage with real-time data integration, which enhances the flexibility of usage of models, the output being the same. This is the difference as compared to LLMs, that we are able to link the data, knowledge base, and business documents, literally of any format, that we are able to link with the querying section in real time. The LLM hence becomes more knowledgeable and able to answer all contexts. So the advantage of RAG models is enhanced accuracy uh, as compared to LLMs. And hence, the hallucination and the penetration attacks also can be reduced. And the scalability is also one of the advantages. And coming to the disadvantage of RAG models, the data drives the accuracy. So the dependency on retrieval quality and indexing systems, those also manipulate the accuracy along with the data, type of data. And latency and complexity of the model are also going to be issues. Applications of generative models. So when it comes to applications, it can be used for multifarious types of data. Text generation can be manipulating question answering or content creation, or chatbots can be created for conversational purposes. Even conversational bots can be specialized to a purpose. For example, a chatbot can be made as a receptionist, or a technical information can be fed to chatbots. It can be specialized in answering, teaching maths or English. Like the range of applications that are spawning from conversational AIs, it is becoming larger and larger. Language translations are also very famous applications in LLMs. Beyond this, the chain of thought models, the few shot programming models, are also helping explanation of answers possible with LLMs. And they are also helping to reduce the the uh, the far-fetched results. They are able to narrow down and focus on the results and provide precise answers. Coming to image generation, image editing, image uh, analysis in literally any field like healthcare, medical imaging, drug discovery, anywhere in art, or just about anything, image generation is being used. For example, if we are able to uh, understand the Picasso model of art, we can give any image and convert it to the style of Picasso. The image generation is also being dragged to security issues with deepfakes. It is becoming a larger issue these days with the penetration of AI in literally any field of our lives. And audio generation, this is becoming literally trendy these days. We are able to hear musicians, singers who are dead long back, even now with the help of audio generation AI. The video generation is also possible with generative AI. Given all the specifications and the prompt, we are able to generate videos and animations in no time. This is going to an extent of creating short videos or short movies with generative AI. So when it comes to text, we are even able to see the usage of LLMs in debugging, documentation, all these things. And so we will now focus on our area of drug generation, drug delivery, these perspectives. So when it comes to generative AI, we are going to deal with medical information now. So when we have generative AI players, they can be pharma players or specialized patients, or diagnostics environment, HCPs, which can optimize the process of personalization of treatments, or customization of medicine, or customization of treatment planning, diagnosis, all these things. The generative AI is in the role of the physician. So these are the AI players that are very much taking the advantage of generative AI. And when it comes to generative AI here this is actually a generic one, which gives the incorporation of text, image, video generation, and data generation in drug discovery. These are few to mention certain players in generative AI who are playing very important role in this genre. Coming to the advantages, strengths, and weaknesses. When it comes to generative AI, we are able to see novelty, creativity, the speed with which they can process human thought stream is being replaced with much lesser time, and the throughput is high compared to the manual process. The flexibility and adaptability, customizability, the reach to a large number of population, decision making, diagnostics, precisions are being the strengths of generative AI. And the weakness being the bias issue, which is going to disrupt the decision or the diagnosis or the choice that we are using as per the process that we are using the model. So when it comes to generative AI, in drug discovery, we can create compounds or protein-based therapeutics, and new drugs can be, delivery systems can be designed, and personalization of treatments can be done. All these are current researches and implementations that are being seen recently. And Huma AI is one of the uh, famous applications which is even existing in market. Applications in medical affairs, as we look at it, medical content generation, like we are able to see for summarization of medical articles and reading the content. For that, medical content generation AI is very helpful. Medical data analysis and diagnosis, prognosis, medical information, and education with the help of conversational agents, that is also very much prevalent. We are seeing to an extent, like if you are able to load an X-ray to a conversational agent, it can tell the severity of the X-ray, like where the damage is, how much is the damage, is it a hair file crack or is it a larger one, acute case. It can answer to that extent. And we are able to see key opinion leaders, the KOL identification, and people who are all working on it and who can collaborate, what ideologies they are having. Those can be summarized with generative AI tools, and innovation and novelty can be, the pace can be fastened. And medical event planning is also very much possible with these tools. Generative AI can provide a lot of advantages like rapid synthesis. For example, in the period of Corona, the development of vaccines used to take literally 10 years, but at the pace uh, the drugs were developed during these years is much faster, and it is also to the advantage of serving huge amounts of population in very less cost. And that rapid synthesis is very much geared by the generative AI, and the interpretation of vast amount of data, which is literally non-comprehensible to a normal human. It requires a lot of expertise that can be replaced by generative AI, and the time management, of course. And when it comes to clinical trials, that information, if it is being logged as EHRs. It can also be analyzed, and recommendations can be made for visits, or notifications can be done, and uh, we can go ahead and use it to literally any extent. Coming to generative AI, it can also be used for marketing, drugs, and branding. As is the case of Novartis, they are using AI for brand generation, identifying the brand names for their drugs and launching them in a beneficial way. And Merck and Co, they implemented a chatbot called Carla. This is to improve the customer service for their drugs. And applications of generative AI are not restricted to what we see on the slide. This is for customer segmentation, sales and training, sales performance analysis, uh, planning, sales content generation, all this, but it is not restricted to these cases. And when it comes to applications in sales, so this is of least important to us. So we just go ahead. Coming to generative AI, we can use um, them in drug discovery. Now we reach our focus area. So AI can be used in drug design with molecules being modeled in 2D or 3D structures. The protein interactions can be predicted, drug protein interactions can be predicted, the response, the potency of drugs can be analyzed and predicted. That can help in drug discovery and manufacturing. It can also be used in polypharmacology, designing bio-specific drug molecules and multi-target drug molecules. For example, we are able to synthesize one drug which can be a vaccine to children for 5 different issues. We are able to generate drugs. For example, it gives a possibility of generating one drug for maybe cancer and Alzheimer's together. So that polypharmacology is also becoming famous these days. Initially, we used to give several vaccines for children, but now just one medicine, one syringe with several vaccines. So that is how it is advancing. AI can also be used in chemical synthesis. We are able to predict the reaction, the yield, the targets, all these things can be analyzed in a much faster way. Drug repurposing is also possible, like using one drug in a very different purpose, like a very different situation. Maybe like one drug used for a different purpose, like allergy or some other symptom. And drug screening. So predicting the toxicity, bioactivity, all these things are also possible with AI. And coming to AI in drug development, the advantage is expensive and time-consuming nature of the process that is being patched by AI. We are able to accelerate drug discovery by the using of the data. And when it comes to generative AI in drug discovery, accelerated drug discovery is the major advantage, which helps in faster uh, development of drugs, even for new diseases. Cost saving nature, targeting rare diseases. Now we are able to analyze large genomic sequences of protein molecular structures, all of them with a computational power that we have. So that we can generate medicine for very rare diseases. Drug screening and prediction of the response is also becoming very much possible these days. The need for AI in drug development is being summarized in the slide. growing complexity of drug development, we are focusing on the the problems like as we discussed, polypharmacology, which involves multi-targeted drugs. This being the demand, we are synthesizing drugs for several purposes. We are repurposing them. A lot of things are happening, and that demand is being satisfied by the use of AI. And we are able to handle large information in very many types of data, uh, probably genomic sequences as a text, the molecular structures as maybe graphs or just anything. All together, multimodal analysis can still be made possible. And here we are able to perform target identification. We will discuss exactly what these terms are and what these terms actually mean in discovery of drugs. So we will revisit the slide. So we are able to see we can use AI in target identification, lead discovery, lead optimization, preclinical testing, clinical trials, and regulations. So this is a basic structure of what we will be discussing. Like when there is a molecule, the compound, we are able to portray it, encode it in proper notations, form data sets, convert them to data sets, and we are able to apply models for predicting which targets are being affected by the medicine and which medicines are having what type of response. All this can be done with classification, feature analysis, prediction, all these things. So this is the framework that we are actually discussing. And we will start with the encoding of data. SMILES is a notation. It is simplified molecular input line entry system. It is a notation of encoding components in a linear way. For example, if we have the last line, which shows cyclohexane as a sequence, but the actual compound is depicted in a much complicated way. We need to address representation of atom bonds between the atoms, the branching, the parenthesis notations, and the ring notation, representation of numbers. If it is 4, C4 can be given as CCCC, and such ring notations can be given. And aromaticity, the lowercase letters, that is going to denote the aromatic atoms. And stereochemistry, like when we come to the configuration of how the direction of alignment of the compound is, that is depicted in the SMILES notation. We are able to give isotopes in specific formats, the charge of the atoms in specific formats. All this is being given with examples. For example, aspirin is given in the SMILE notation over here. So SMILE notation is able to, it is actually the notation which when fed into AI models, it can be helping to identify the bioactivity, like which parts are being affected, what is the reaction of the drug, what is the toxicity, solubility, ADMET. These are features, short form. This means that absorption, distribution, metabolism, excretion, and toxicity. For example, okay, we will discuss this later. And graph neural networks, transformers, these are models which can process smile notation. Specific LLMs can be created, CLMs can be created, chemical language models can be created to have been created to process smiles notations. So this is the encoding of the data. So what are targets? The target types can be enzymes, receptors, the channels, transporters of DNA, RNA, genomic sequences. The drug action, is it going to inhibit something or provoke certain actions? It is going to block pain or what? All these are being the targets. The DNA and RNA, is it going to kill cancer cells or something else? These functions of drugs are being depicted by the drug targets. The drug target interactions from the bonds, the covalent bondings, hydrogen bondings, ionic interactions, and all these type of bondings, the strength of the bond can be identified in order to process analyze the activity, bioactivity of the drugs and the potency of the drugs. So what is potency of the drug? When we come to discuss potency, it is the amount of drug that would be needed to get the effect that we want. For example, suppress pain maybe, or suppress fever maybe. So how much amount of drug is actually needed? Is it going to be a low dose or high dose? All this comes into potency. And drug activity is the effect that it produces on the body. The activity is also assessed from the potency. And coming to examples of drug target interaction, this is aspirin, aspirin being a painkiller. So the target, we have identified this cyclooxygenase as the target. The interaction being a covalent bond, like with this target, it is providing a covalent bond and thereby reducing the pain. So this sort of analysis is drug target interaction. And coming to the application of generative AI, there are so many areas in drug development. For example, molecule design. Generative AI can be used to generate molecules in a specific pattern that we are looking for. This is an example. For example, a medicine for a course will suppress fever in 3 days. That is the design requirement. So that is being dictated in the example. And molecular property prediction. Neural network predict the solubility, the toxicity, the potency, the bioactivity. All these properties are being predicted by the models. Drug repurposing, like for existing drugs, what are the new uses we can identify? Molecule simulations. Molecule simulations, one added mention about quantum technology, quantum mechanics, quantum AI. It is also becoming popular, which can uh, see drug discovery, protein analysis. All this has been considered really complex with the advent of quantum technologies, quantum AI technologies that can be uh, taken to the next level. The time can be reduced. The number of components that we analyze as permutations can be increased to a large extent, which will increase further the pace of drug development. And we may have a disease-free uh, population in near future. And optimization of drugs. Like drug properties, we saw ADMET, solubility, toxicity, and so many other properties. They can also be uh, manipulated with machine learning models and found out, predicted. And screening, AI screens databases for compounds which have high affinity for a target protein. For this target protein, this compound will react well. That type of screening, searching can be done at a much lesser time using generative AI. Compound library expansions. When we have so many chemical structures, diverse data, we can use models which we discussed earlier for generative AI in order to find proper drug candidates which can be used to provide proper medication. Finding the biomarkers, the exact gene gene sections which will affect, which are being affected by a disease, which are being cured by a drug. All this is being able to analyze by the help of AI, and analyzing the pathways, biological pathways, how the disease progresses and how the medication, the drug affects the subjects. Automating the synthesis planning, how much scalable the production of drug candidates can be, even in manufacturing and planning, all this AI can come to the rescue. Reuse of currently available medication, repurposing, those can very well be done with the new disease scenarios like during COVID-19 pandemic. Initially, we did not know vaccines, so we were looking for drugs which could presently suppress the symptoms of COVID. So such reuse scenarios can be met with generative AI. Multi-target drug discovery, as we discussed earlier, multiple biological pathways can be identified for one drug, and we are able to cure several diseases with just one drug. And improving the efficiency of lead generation. When it comes to leads, lead is a technical term which means that when we are testing the bioactivity of a drug, there are certain hits which are going to identify the success rates over several episodic manner, in several episodic manner. So hit identification leads to lead generation. So we are getting a promising compound for a drug. That means lead generation. And optimizing the compound, being able to identify the safety component of the compound, the selectivity of the compound, that is lead optimization. So this is lead generation. So we are able to identify the compound for with virtual screening, and we are able to apply the generative models and identify the compounds which are possible, not just one. Several compounds can be identified with the models, and we can test out from all of them which is the most suitable one, which will be helpful in manufacturing a drug. When it comes to generative AI frameworks, variational encoders, generative adversarial networks, so most of them are discussed earlier. So go ahead. The challenges in the incorporation of AI in drug development is the limitation of the data. This is not just any data. This is specific data which hails from several experimentation and heuristics. That being limited in nature is the major issue, and the quality of data is also a concern. Optimization needs a lot of hardware support. Computational complexity is also a concern. And the opportunities that we have, we are able to generate drugs at a much faster pace. This is GNN, very widely used in drug analysis, graph structures in 2D and 3D format. Graphs are made up of vertices and edges. This is an example. So we are able to identify a molecule and we are able to represent it as a graph and a compound that represents a drug as a graph network. And that network is being subjected to computational models with artificial intelligence. So we are generating molecules, we are calculating several parameters that we discussed, like ADMET, and we are able to analyze which are the uh, leads that are promising for candidate drug generation. So leads are nothing but compounds that are promising to create a drug. It can be at first stage, we can identify some 10 components as leads, and from them we will test out and just segregate very few for candidate drug generation. CNNs, these are convolutional neural networks. Basically, neural networks, they are used for feature extraction using the convolution pooling and fully connected nature. So here also using the input uh, images being applied with the convolution and pooling. Convolution is going to focus on certain area, apply certain functions, and summary of that is put up in pooling. And when we are discussing literally all possible combinations, fully connected layers come into picture. All possible permutations and combinations of compounds are being tested with fully connected layers. And coming to RNNs, uh, recurrent neural networks, these are very good at sequential data analysis. So if it is a high dimensional molecular data sequence analysis, that can be very well done with RNNs. So just assume that the X1, X2, X3, all these are components from the compound that we are actually analyzing. So the drug interaction, all that is being analyzed here. And reinforcement learning is machine learning models can be segregated to three types: supervised, unsupervised, and reinforcement learning models. And reinforcement learning is very close to the learning of human brain. Like when a child literally does not know anything, touches a fire, it feels fire and retreats back. That is cognition. It is learning by cognition, by experiences. So the external environment is imposing certain actions are happening as consequent to these actions, and the policy can be drafted for response, uh, which will optimize, like reaching a goal. For example, our context is optimized drugs leads can be identified. So this is a reinforcement learning based drug development model wherein we are analyzing compounds, molecular compounds, which are uh, possible candidates for drug development. We are testing them for certain interactions, target interactions, and then we are identifying if they are reacting well or not. If then rewards are given, else punishments are imposed in an episodic way, we are making a summation and we are able to optimize the actions towards drug development. And transformer models can still be applied to drug discovery. And as we discussed earlier, LLMs specific to this is an example. Specific, we'll come to this later. This is a diagram which shows CLM. It is a chemical language model. It takes smile notation as input, and that not being the only form. We can go for deep spans model of selfies model, which is an embedding. See, NLP, as happened in the previous session, NLP deals with text, not generally text. Text is converted to vector format, text, the frequencies, text document frequencies, inverse text document frequencies, end-to-end analysis, the word embeddings, semantic embeddings. They are converted to embeddings for faster which are quantified models. So text is not limited to it. So the chemical notations are also converted to embeddings. That is also going to fasten the pace of analysis. So CLMs are going to take any of these and analyze these by incorporating machine learning models. So this is what it means about incorporation of the elements. And we will go for a little demonstration. So this is using RDKit, which is a package for analysis of chemical compounds. RDKit package. There I have shared a document with ma'am, which contains just very few functions which are just going to kickstart your analysis on this topic. So this basically is about installation of RDKit, and this is about converting the SMILES component. See, this is SMILES notation of aspirin, the drug aspirin. So it is encoded in SMILES notation. We are trying to analyze its molecular descriptors like the molecular weight, the hydrogen bond donors acceptors, such and such components we are analyzing here. And this is checking drug likeliness. When we have to consider a compound for a drug, there is a rule, a Lipinski rule of 5, which satisfies these parameters. These are the bounds that are being specified by Lipinski to consider any compound for suitability of a drug. So this is a function that takes into account, actually we are analyzing aspirin here. We are considering it, the upper bounds that are being stated in the Lipinski rule, and we are analyzing aspirin, and we identify that it is sufficing the criteria of the drug. And this is pre-processing the data set. Loading and pre-processing the data set. This is actually the data. See quickly, this I have generated out of a few steps. This contains, you can see one cell with the canonical SMILES, which is the SMILE notation for that compound. The data validity description, this is one of the descriptions, which says values for this activity type are unusually large or small, so may not be accurate. This is just a descriptor adding to the analysis. and the ChemBL ID document in which these are coming from, the documented year, ChemBL ID, what is the standard, the standard is the potency value. It is the standard way of representing the potency concept that we discussed earlier. IC50, as we see in that table, it is the concentration of a drug to inhibit 50% of specific biological process. It is saying that it is going to lower that activity of the drug of the disease. This drug is going to lower the activity of the disease by 50%, and during a course will avoid the disease. So this is actually the depiction. There are several depictions like EC50, KDKI, inhibition constant, dissociation constant, half maximally inhibitory concentration, half maximally effective concentration, all these things. That is being stated here. So just few to mention, a lot of such things. What is the target preferred name? So where is it going to, which tissue is it going to affect, all those things? So what do we see here? We are taking the canonical SMILES value. We are filtering it. The activity comes from the data frame column, filtering out just this IC50. It is going to take these potency or the drug compounds with this potency. So it is doing a filtering there. So that is being done there. So it is filtering out all of them, the drug compounds with this potency, and this is listing. So now we'll have to apply machine learning. And here we are converting SMILES to molecular fingerprints. We are transforming to another format, chemical structure format. And here, this is as a vector. Morgan fingerprint is a notation that comes with the package. This is all inbuilt into the package. So it is being loaded, and then we are applying a model, random forest model here over the data. The model is typical. It can be like as we apply to anything. So it is saying that the predicted activity, it is active or passive. So it is stating that it is active. It is going to cause some reaction, and in a good way. So it is giving for the input that we give. It is predicting how it will react. So that is being done here. I would like to show two tutorials. This is a tutorial which uses data commons package. You can see the flow here. This is going to rank the candidate compounds, drugs. Okay, we will go through the collab, and then we create this one. So this is data commons package. We are able to put up queries regarding this is a query. Name, where, a type of disease, common name. So we are selecting a disease and putting it to a query. And here the disease ID that is being filtered out, and what all the treatments and which type of chemical compounds are used for the treatment for this disease, that is being put in this query. And this is the list of all such compounds. Are they going to, we have taken a list of such drugs now, and are they going to contradict each other? That is being tested in this section. Chemical compound contradiction, disease contradiction. Is it going to lead the disease as such or promote the disease, or is it going to suppress? So this is disease gene association, which genes are associated. That is being filtered by this query. So you can see a select query here. We are able to see the gene associations for every compound that we found out. And here we are trying to find the chemical compound gene association. So which genes are associated with this chemical compound that being said. And then, so which drug is actually cure to that particular disease. We are selecting particular candidates, and who is the manufacturer. These are candidate diseases for this. This is the target list. And this data commons along with the RD kit, which we discussed earlier. RD kit is very famous package for analysis of drugs, chemical compounds. So for this Miles notation, given this Miles notation in the drug, what is going to be the molecular compound for this candidate? This is the Miles notation. This is the affected gene. This is filtered. And what are all similar other things that is also filtered out with timing to similarity. This is a metric, and this is ranking based on similarity. On that timing to similarity, we are ranking them. This is a function for it. So Tanimoto gives a similarity coefficient. So with that, it is being ranked, and this is visualization of the chemical compound as a graph. This is the structure visualization using the package, and analyzing the compounds which are suitable for that disease. We started off with the disease. The ChemBL is a representation, and here we are just filtering them out. For that drug, who is the manufacturer? In what state is that drug? Is it being marketed, or is it applied state? That we are analyzing. So this is one tutorial, which is, we will go for another. These are all freely available. The one we discussed now is provided by Christy Lincoln and Samantha Pecos. This is on drug discovery with data commons. This is being available in internet, and this is another channel. You can find it in GitHub Data Professor. Here, the entire tutorial of using RDKit in drug discovery is being summarized here. We'll just mention very few. We will just go through the session. So this is bioactivity, downloading the data and analyzing the data. That is being done here. ChemBL resources are being used here. That is being so which target proteins are being affected for coronavirus? Which are the targets in humans? Because it can be affecting rats, it can be affecting humans. In them, which target proteins are being affected? That is being filtered out over here. And for SARS coronavirus, for that, what is the bioactivity data? So this is a compound. This is a compound which will inhibit the concentration of SARS. So this is being done here. So we are saving that data. Pre-processing that data. Bioactivity data, is it inactive, active, or intermediate? That is being done here. Actually, that is what we did in the previous tutorial reviewed in the document. So we filtered out IC50 units, and from that we went ahead and collated all the components, and we found them like which are active. So that is what we did. It goes to the comparison, the if-else comparisons. So it goes on like this. You can see lots of EDAs, exploratory data analysis over here. This is very much into drug discovery, but also lots technical. So this is application of regression models using random forest for drug discovery. So all this is going to be available in this link. So as a summary, go back to the slides which we left out earlier. So this is what we skipped earlier. So we are able to, for when we apply generative AI for discovery of drugs, we are able to segregate molecules, their simulations with the parameters, the added parameters, the optimization of drugs, lead components and their optimization and their incorporation as drugs, their response being active, inactive, that can be done. And the pathways, like what parts of the body literally are being affected, that is being analyzed, and how we can repurpose or multi-associative drugs can be developed. That can be done with generative AI, finding the biomarkers, analyzing the gene sequences, and the response of the drugs over them. All this is literally possible with generative AI, which is becoming much faster these days. And so maybe in near future, we will be able to develop drugs for a lot of diseases which are uncurable these days. And we are already witnessing Russia being able to claim that they have discovered the cure for cancer. So such marvels are being able to generate the process of discovery, and so this is ultimately the usage of models in drug discovery. We are able to identify the compounds where they affect, those are the targets. So if we are getting hits, then we are taking components for lead and we are optimizing those leads. Leads are nothing but compounds, not just one, several candidate compounds. So which one can become a potential drug, that is done after lead optimization. And then we go for clinical testing and then clinical trials. And then only we can confirm that we have found the drug. So this is how it goes in every stage of drug development in this pathway. We are able to use generative AI. So with this, we will close this session. So any queries, we will discuss them.
Participants, you may put your questions in chat box. We have got a good feedback only. Till now, I didn't get any queries and any questions. Hope so. I would like to thank you for accepting our invitations and also giving the lectures in the topic of AI in drug discovery. How this new generative AI helps in this drug discovery for the new medications. You have given a good given a the insights to the participants. It may help to the participants, those who are all doing the research in this domain. It may help you. And also, I have got one question in a chat box, ma'am. I'm reading the same. How to implement in experiments?
Uh, so if you are interested, experimentation, no, we are bothered about data analysis. So provided we get the data from medical sources, from that only we can go for applying the model. So the model is going to be literally this, as we discussed earlier. As we discussed earlier, provided the data, we can go ahead and apply the model and find out what is going to be the for that particular disease, what is the target, all these things. So we need the data which can be downloaded from databases like ChemDL. I will just show it.
The question is one more question, ma'am.
There are databases like MDL. If you want to just go for analyzing with whatever data is available, these are databases. These are databases. So you can see ChemBL data, it goes ahead and gives drug-like properties from bioactive molecules. It is able to give chemical bioactivity, genomic data, all this. So you can download this data and therefrom you can apply the model and try out drug discovery models. And definitely it will need more data from actual medical environments. So if, just for practice, you can just go ahead and use these and you can go ahead and test them out. There are so many such databases. For example, just a second. This is ChemDL database, and there are so many other sites also where you can find the databases. See, farm GKB. This is used for drug gene association. Every database will have its own purpose. You can associate all of them and do a multimodal model. This is for disease ontology. And these are all different databases. This is for disease ontology. We will explore the sites. So it provides UI like this, providing the disease ontology. This is a knowledge base. All this is information. All together you can analyze. And for your particular purpose, you may be analyzing maybe diabetes, maybe any other disease. So if pertaining to that disease, these contain data, now you can continue with even multimodal analysis. I think that answers your questions.
Ma'am, I
Any,
hope they will
any
get
more
the answers. One more question from Ram Kumar. Rakesh, to what extent virtual screening handles the key challenges in predicting drug efficacy and toxicity?
Actually, it depends upon the data only. As we went ahead and discussed earlier, the limitation of usage of generative models in drug discovery is dependent on the data and the data quality. Only then we can go for screening. So the efficiency of screening as such is dependent on the data. So what data we have, from that only we can precisely get the proper results. So I will go with that as the answer. Any more questions? Any more questions?
Ma'am, can you hear me, ma'am?
Yes, ma'am. Yes.
Yes. So, ma'am, one more question.
Hmm.
How do we implement this kind of concepts in the student projects?
It is simple, ma'am. You can go for using these databases as you can look at these tutorials. You can start with these tutorials. This is a very good place. Data Professor is a very good place. It uses ChemDL dataset. Dataset, you need dataset for analysis of drugs for any disease. No? So you can take up this goes with ChemDL dataset. So it gives certain features only bioactivity and certain other features. Not everything will be available. Gene association, you have to go for another dataset. So this you will have to choose the appropriate data set and then the disease and what you're trying to do. Identify the compound or what you are actually targeting. Like for diabetes, are you trying to go for a cure, a drug which will suppress what? Because there are so many diseases associated with diabetes. So being that as the question, hypothesis should be framed, and that in mind you have to take the data set and apply the model as the flow we discussed. And this is already in Smiles notation only. And it is the package, the RD kit, it is already able to process Smiles notation. So you will need only the package like RD kit. With these, this is a very good place to start. You just go for GitHub and go to Data Professor channel. There you will see all these tutorials. And therefrom you can start your research. There are so many such data sets. I told you few, ChemBL, this thing called disease ontology, and few other things also. And so many others you can find. So with that, you can do student projects.
Thank you, ma'am. They have got answer, I think. Uh, ma'am.
Yes, ma'am.
Yes, ma'am.
Any more questions?
Yeah, no, ma'am. No more questions. Give few topics of projects. Again, Meena Mittal have
Topics.
raised the question. Give few topics because this will be the new topics, emerging areas. That is the thing they were getting the. They were want to know the titles and also.
Topics. I would suggest you to look into each of these itself as a topic. Drug repurposing is a good topic. Using graph neural networks, GNNs, to identify the activity, the bioactivity, and the affinity of the compounds. That is also a good topic. Each and everything that we listed here, going ahead and finding, predicting the molecular property, drug repurposing, optimization, lead optimization. That is also a very good topic. For a particular disease, you can go for this. And biomarkers, working with biomarkers, it is a very good topic. Associating gene associations and the drugs, that is a very good topic. Pathways is a very good topic because multiple pathways, if you find, then you will find a cure for several diseases with one drug. So these are all possible topics which you can probe. So the applications, as we discussed, these are all actually topics for your work. Multi-target drug discovery. These are all actually topics. For any particular disease, you can go ahead and start working on these things.
And one more question.
Yes,
Can you please highlight the use of disease ontology? How to implement it practically, integrating generative models with disease ontology?
disease ontology actually gives associations of diseases, like which are symptoms of these things. As such, it is not the ultimate solution. That can be took as one of the data sets. Uh, it can be used as one of the information in these things. See, this is the data set. This is ontology. This gives you all this information. The disease related infectious agents, all these things, and the association between the diseases. So this itself is the purpose of disease ontology. You can go for even visualization with these information. So that is what you can do with this thing. The metabolic disease, genetic diseases, their information. See, it can be, this is also an online tool. I'm expanding one by one. So you can analyze which chromosomes are infecting, causing, affected with the infection. Such a biomarkers study can be done with this thing, ontology.
Hope they will get the answer, ma'am.
In what there is.
Queries is one more question. Able to implement in Python, I think.
Yes, definitely. This is
Yes.
completely Python only. What
Yeah.
I showed you in the document,
Yeah,
but with different packages. RDKit is one of the package. Data Commons is another package. This is completely Python only. RDKit package. Python is more than enough to start But with these packages, you can do a decent work.
Yes, ma'am. Sure, ma'am. I thought you give a brief intro about this generative AI in discover that is drug management. Many researchers and many academicians get to know the thing to explore in this domain, ma'am. I hope, and also performance evaluation, how it is done. On my question.
Performance actually, model, no, the performance metrics are not going to be any different. It is accuracy. Here, in correlation with the drugs, we are able to find if the compound is going to be active, inactive, or it is that way. So that will be what, in association with drugs, only these decisions we can grasp. The molecular descriptors, these compound association, and whether that compound is going to be active for that disease, that only we can find it. But for the model as such, any ML model will have accuracy, precision, recall, those things as the parametrics. But then associating that with drug discovery, you know, these are going to be the inferences, or as you call performance analysis metrics.
I think again, ma'am has asked the question. Any research paper which can be referred? Hope,
Research
hopefully, we have to
paper.
refer the research paper.
Actually, I prepared the slide with a lot of research papers. I will just show one. This is actually a survey paper, and you can find a lot on PubMed also. This is a summarization of the frameworks which are used for drug discovery, but this gives you only the survey of all the models in corporation with association of drug discovery. But then PubMed gives a lot of implementations also. And I think there are a lot of implementations. As I'm projecting, this is one of the literature survey papers, open access for beginning. But then other papers are also available.
Yes, ma'am. Thank you, ma'am. Thank you for sharing your knowledge with us, and thank you for spending your valuable time with us. Thank you so much, ma'am, once again.
Thank you, ma'am. At this evening time, we have a lot of participants. I thank all of them for spending their valuable time for discussion of this topic. Thank you all.
Thank you, ma'am. Thank you.
Thank you, ma'am. We'll close the session.
Yes, ma'am.
Mhm.
Participants, I have posted the feedback link in your chat box and also in the WhatsApp group. It is available. Please fill your feedback for today's session. Thank you. Thank you so much for your participation, active participation. Thank you so much once again.